So today I will talk about a topic called deep boundary aware semantic image segmentation. Okay, so this is a joint work by Shenzhen University and the Hong Kong Polytechnic University. Okay, so the work is generally done by the two students, Yifan, Chen, and supervised by Huisi and me, also with the help of the Dr. Xueting Liu. Okay, so if there are any questions, so you can contact me. Of course, I want to thank all of you share this CASA, okay, 2021. It's very nice conference. Okay, so generally I will give some introduction, then I will talk about our methods and main contributions. Okay, so then there will be a conclusion and further Q&A. Okay. So of course, currently the semantic image segmentation is very important topics and have great impact. Okay, so if you can do this kind of thing very well, of course you can do the following other things better. For example, if some people working on image video colorization, okay, so if you can do semantic segmentation very well, the image video colorization can be further enhanced. So this is basically a fundamental work. Okay, so of course there are traditional methods, also the learning-based methods. Okay, so however, recently the CNN-based method, convolutional neural network, has significantly improved the semantic image segmentation. Okay, so however, the state-of-the-art method, the best methods currently suffers from the blurry boundaries. Okay, also the mismatch by different multiple scale objects. Okay, there are many challenging issues, but there are two main key challenges. Okay, so the performance of the existing multi-scale modulars in the existing semantic segmentation method still relatively have limitations. Okay, when dealing with multi-scale objects, especially at the blurry boundaries. Okay, so of course it is also very challenging to identify the clear boundaries, of course, clearly and efficiently, accurately between different multiple scale objects. Okay. So the right side show you some examples of the semantic segmentation. Of course, this is the general level. Of course, you can do better things like the how to say it is not better, more detailed things like instance level segmentation. But here we do not work on instance level, so we just try to for the general semantic segmentation. So we try to enhance the performance. Okay, so the performance, the key when you are doing researches, so the motivation is really important. Okay, so basically we wanted to solve the challenge issues, which means we focus on some existing real problems. Okay, so the existing method for the state-of-the-art current work. Okay, so they still could not process the multiple scale objects, especially the small scale objects very well. Okay, also for the boundaries, especially there are multiple objects, so the boundaries are very complicated. Okay, so it is difficult or very hard to identify the clear boundaries between different multiple scale objects. Okay. So of course we want to solve this. So basically we propose a new two-branch networks. Okay, so for the image semantic segmentation, of course later we want to extend it to the video domain. Okay, so so in this way, so the two branch means we have the one branch is a multi-scale modular for capturing the multi-scale information. Okay, and there is a boundary modular, which means the second modular, so to catch the complicated boundary information. Okay, so we try to integrate the self-attention mechanism, okay, or can be called self-attention context, okay. So with ASPP, the actual spatial pyramid pooling, okay, to the multi-scale modular, which means our first modular, to enhance the expressive capability of our semantic segmentation network. Okay, so we propose a new boundary modular, which means the second modular. Okay, with FFL feature fusion layer to fuse different levels of features, which means low-level features and high-level features. Okay, of course we can extend it to many more multiple levels of features to extracting the more accurate, clear boundaries. Okay. Okay, so this is the overview of our two-branch network architecture. So you can see that they are basically two parts, the top part and the bottom part. Okay, the top part is the multi-scale modular. The bottom part is the boundary modular. Okay, so the multi-scale modular basically use attention mechanism, especially the self-attention context. So we call SAC. So the boundary modular, which means the bottom one, so basically use FFL feature fusion layer to fuse the low level and high level features. So basically you can see that our network basically have two branches. So one a multi-scale modular to capture the multi-scale context information through the multi-scale modular. Okay, another modular is the bottom one, so it's the boundary modular to capture the complicated boundary information through the boundary modular with feature fusion layer FFL. So okay, so this is an overview. So then we can go to our first modular, which is top one. So for the multi-scale object semantic segmentation, okay, so use SAC, we call self-attention context modular, okay. So in this modular, so basically our main ideas focus on to integrate the attention mechanism, self-attention mechanism, okay, with ASPP, Assured Spatial Pyramid Pooling, to enhance the multiple scale object detection. So you can say that you can work on multiple scales object detection. So what is the meaning? Okay, so the meaning is that if you for the large scale object, it is quite large. So it's the boundary usually is clear, so it is not a problem. So usually the multiple scale is especially good for the small scale object. So for the if you can solve for the problem for the small scale object, of course it is not hard for the easy problem, right? Okay, so then we have the second modular called the boundary modular, use feature fusion layer. Okay, so of course we can have the high level features, we can have low level features, which means for the high level features there are also multiple features. For the low level features there are also multiple features. So which means for the we divided them into two categories, and then we fuse the two type of features. So actually there are multiple low-level features and multiple high-level features. Then we fuse them to design our FFL feature fusion layer to generate our high-quality boundary aware semantic segmentation. Okay, so of course later, so we will work on the instance level. So instance level, it is not a difficult problem. It's just we separate the work into two stages, so then we can do each stage very well. Okay. So of course, in addition to the experiments, so we need to do ablation study. So usually this is this is not a problem in the previous traditional method. However, in the deep learning stage nowadays, so the ablation study is very important. If your paper do not have ablation study, it is almost impossible for your paper to be accepted by any top conference or top journal. Okay, so this is a visual comparison for with and without multi-scale streams, which is our first modular. Okay, so the left side show you two cases of the input images. Okay, the second column show you the ground truth, which means the true semantic segmentation. Okay, so the C and D show you the semantic segmentation without and with multi-scale streams or multi-scale modulus of our method. Okay, so you can see we use rectangles, different colors of rectangles to indicate different areas. So you can see that the comparison between the with and without multiple scale streams. So you can see especially for the small scale objects, we enlarge them. So you can see clearly that there is obvious difference and it is much more close to the ground truth. Okay, so which means the method is meaningful to have a multiple scale streams, especially for small scale, extremely small scale objects. Okay, so this is a visual comparison for the with and without the boundary streams. So of course, the A also show you the two input images, and B show you the ground truth of the semantic segmentation, and C and D show you the, of course, C is without boundary stream, and D is with boundary streams. Also, you can see that with this streams, so you can see that for the boundary area, especially the boundary area for the very small objects in the enlarged rectangles, okay, so you can see that there are obvious difference, okay, so much better compared with C. So D show you the case with the semantic segmentation with boundary aware optimization, okay, so much better results. So this is actually very basic research in computer vision and computer graphics. So you need to compare with state of the art baseline. So we use state of art work as the baseline. So compared with the baseline, so we can add the multiple scale streams. MS means multiple scale streams, and BM means boundary modulus. Okay, so with the boundary stream and the multiple scale stream, so you can see that the results are enhanced. Okay, with both of them, so it's much more enhanced. So which means compared with the state of the art, so with two different type of networks, so you can see that our using the measure of the mean IOU matrix, so the ablation study showed that our quantitative evaluations also have the best performance. Okay, so in addition to the quantitative comparison, so we also work on the visual comparison because we do visual computing in the computer animation and social agent, right? So you need to, in addition to the quantitative and qualitative comparison, you also need to compare the visual effects. So this is the visual comparison with different state of the art work, also with the ground truth. So you can see that for our work, so which is mostly compared with the existing works, it is mostly close to the ground truth segmentation. Okay, so of course this is not in every case. But in the most of the cases, so we have the best performance with the visual quality enhanced. Okay, perceived by human beings. Okay, so this is we do comprehensive quantitative evaluation. Okay, so the quantitative comparison of our method, also we use IOU, the intersection of union matrix over different category of images. Okay, compared with also the state of the art works. Okay, so you can see that in the most of the categories, our method achieve the best results, but not in all of them. Some of them, some method have better performance in some category. Okay, so we can just say that in the most of the categories we have the best performance. Okay. So actually, this is also the limitation of most of the works in semantic segmentation. So you need to, if you have a general method, you cannot work for all. So if you have a specialized method designed for example, sky, then I work on sky, so I have the best results. Right? So, however, if you have a general method for everything, you can work on car, work on sky, work on truck, work on bus. So it is not possible. Usually, it's not possible for you to have the best performance in everywhere. However, in our work, we focus on the small multiple scale object, especially for the small scale object. It's also for the boundary aware operations. So at this side, so for the visual comparisons, that our method have the best performance at a small scale and the boundary information blurry boundary informations. Okay. So this is the visualization for our main contributions, that the boundary map prediction. Okay, so show you the boundary maps of the input images. So you can see that the results of our boundary map prediction is really accurate, and it would be very helpful for further applications like the image video classification or further instance level segmentation for semantics. Okay. So, and because we have the boundary aware operations, so previous impossible boundaries, like the you can see the down left side image. So there is two cars, not one car. So, and two people, two persons overlapping. Okay, so then you can see the boundaries for the two cars and the person together. It's very well illustrated. So this will be very helpful in the further processing. Okay, so for the conclusion, so generally we propose a new two-stream network architecture, or you can say two-branch for the semantic segmentation, okay, with the multiple scale stream and the boundary stream. So the multiple scale stream will extract the multiple scale context information, especially designed for multi-scale objects. And the boundary streams will be used for extract the complicated boundary informations. So with these two streams, so our semantic segmentation for the general design is quite enhanced, and the results is quite impressive. So we also proposed to introduce the SAC, self-attention context modular, which is the attention mechanism, so very popular recently, okay, together with the ASBP, across spatial prefix pooling modular. Okay, so with these two modulars, so we enhanced the multiple scale streams. So this is a new try, but this really works. Okay, so we further propose a new feature fusion layer. So the FFL, we call FFL. So we fuse the multiple low-level features with multiple high-level features. Then these multiple low and high-level features together help us further enhancing the semantic boundaries in semantic segmentation. So I think especially consider the semantic boundaries. It is really a very new idea. Okay, so of course, our method significantly improved the segmentation performance on the small object semantic segmentation due to the multiple scale streams or modulars, and we can predict the boundary of the multiple objects much more accurately and clearly due to the boundary modulars, which is our second modulus. Okay. So, but you say whether your method is perfect for the general semantic segmentation. So it's not actually. So we tested it, and for something that is the image quality is not very high, or the boundary is really complicated, the lighting information is not very good. You can see the top and the bottom input images, top left and bottom left. So you can see that the lighting condition is not very good, and the images resolution is also not very high. So then you can see compared with the ground truth, so there will be some problems at the boundary. So which means our work will also fail in some extremely complicated boundary cases. But this is a good news. I consider this thing as good news when doing research. So you can fail in some failure cases, so which means you can further enhance it to make much better papers in the next stages. Okay, so we are working on this to solve these limitations. So for the complicated, extremely complicated boundary informations. Okay, so also we are extending it to the video domain. So for the videos, so the pixel temporal consistency you need to consider for this kind of thing. Okay, so thank you very much. So if there are any questions, so you can ask.
Okay, thank you very much.
Thank you, Professor Guo.
Yeah, I mean, we can wait some time before.
I just wonder would you mind to show the quantitative comparison page?
Comparison, right?
Yeah. Quantitative. Where you compared the
yeah.
yes, here.
Yeah, we achieved the best results in the load and in the s.work and s.work not best, the building.
Because some of them you
Some
got
of them
worse result and some of them you got better result.
Yeah, because
you
we are
analyzed where you got worse and where you got better than compared to previous method? So for example, the small size.
Yeah. I think for the small sized objects type, so we have the much better performance. Yeah, because some of this method they have some spatial design. They have some spatial design for some type, so they can handle some cases, some category better. Okay, so our design actually is general design. So, however, we focus on the boundary and the multiple scale, especially for the small scale objects. So, if the objects are in small scale, so we usually will have better performance. Yeah.
So your method is good for small scale object.
Yeah, especially for small scale and some blurry boundaries. Okay.
Yeah, because I can see like for terrain, your detection is a lot lower.
Yeah. Not because this is not a spatialized method. If we on purposely design a method for that category, then of course we can achieve the best results. Yeah. So we design for everything. So then we can just make sure that we achieve best results for the most of the cases. Yeah. Thank you very much.
Thank you.
Nadia, Professor Nadia. Yeah. Long time no see. Hope to see you, in the some real event, maybe in Genoa or Singapore. Yeah.
It was to the Professor Nadia asked you.
Yeah.
It is Professor Lee, Wilson.
Yeah, because
okay.
Sorry, because you didn't show the screen. I see the Nadia. Sorry.
Nadia has a video.
Yeah, I think we never meet. Yeah. Nadia showed the screen, but didn't talk. You talk, but didn't show the screen.
Yeah, I forgot to turn on my
I have some mistaken. Yeah. This is the problem of online virtual conference. Yeah. So we should have some real conference. Yeah. Thank you.
We have another participant raising his hand. So maybe you can ask questions, right? You want?
I think maybe we can ask.
Can you hear me?
Yes.
Thank you for the opportunity. May we go to the field case page?
Field case.
Yes.
Yeah. Sure.
I noticed that at the bottom row, your cases, the segmentation results seems to losing the geometry information, because it seems to be for human beings it is easy to see the straight line, and we won't have that kind of maybe errors or failures. What do you think where we can introduce this kind of geometry information to make sure that kind of maybe the results better?
Yeah. Actually, for the geometry constraints, so we have worked on this kind of work before. So actually, but for one paper, usually you have one contribution. You should not integrate multiple contributions into one paper, right? So previously, we have worked on these geometry constraints. So actually, geometry constraints can help to enhance the performance in some way. Yeah. So this your suggestion is very useful, and we have tested in other papers that we have achieved good results. Yeah, with the geometry information. Yeah, because the geometry information is really existed in real life, and this is some prior information to our humans. So we can use this as prior information and some geometry constraints into the network to let the network learning. Before learning, so they have already can have some prior information. So this is very helpful. Yeah.
Thank you for your answers and excellent work. Thank you.
Yeah. Thank you very much. Thank you very much for the questions.
Okay, thank you much. Yeah, maybe.